I'm Raymond Toy, and Arthur's been bugging me for years to do a talk here, and I kept putting off. So now I'm here, and maybe I'll keep him off my back for another 10 years. So we're going to do a little bit of background about me, and then we'll talk about the kinds of design decisions we had to do to port CMUCL to, in this case, ARM. And we'll talk about how to get started, what we had to do to get started on it, and then I'll go over some of the implementation details that we had to do. Get a quick update on where the port actually is, and then what's next, what we want to do, and then just some final thoughts. So first of all, I am not a software guy. I'm actually a electrical engineer. I spent most of my career doing physical layer for cell phones. Yeah, that was like 20 years of my life, 25 years of my life. And I do have a funny story from that time. Early on, when I was at GE R&D, there was a digital cellular was coming to the U.S. There was a request for people to submit vocoders for standardization for the cellular system. And since I was working some of the GE that was working on vocoders, we submitted one. And after all the work, they had a big meeting to announce the winner. And, this person, I wasn't there, so I don't, this is secondhand information. But the person got up and says, the winner, there's only 5 companies that actually submitted a vocoder for the contest. So he gets up, says, the winner is Hughes Network. And I guess there's like total silence because everybody had assumed that AT&T would be the winner because at that time they were the ones that submitted the best papers on speech codes. And then the Hughes Network representative stands up and says, that can't be right because our scores are not that good. And it was because they wanted to do it fair. It was a double-blind test. They did a listing test. So, like, you know, of course, in the pandemonium, took them, I think, several hours to figure it all out. And they eventually figured it all out so that actually Motorola was number 1. I don't remember who number 2 was. And GE was tied with NEC for 3. And AT&T was last. So that was a big shock. But then some years later, I happened to talk to someone from AT&T about it, and said he'd look around. And the rumor is that the guys who implemented the vocoder for the competition didn't actually talk to the research guys, so they screwed it up. So that was a pretty big mistake. Okay. Oops. How did I get started with CMUCL? I was actually at Ericsson at the time, and cloning of phones was a big problem then, where people, you know, steal your phone numbers and make phone calls and get charged for it all. So one of the managers asked me to if he could do some kind of authentication scheme. So I looked into that. And of course, you know, with all these authentication schemes, you have to use all kinds of, you know, big number arithmetic. I don't know how, but I knew that Lisp supported big number arithmetic, and I didn't want to write one in C or anything like that. And, you know, it's not interactive. So I I looked at CLIP, GCL, and CMUCL to play around with. And we eventually made something and shipped that out. As far as I know, it worked. And then, you know, after playing around with it for a while, I thought, oh, this is pretty cool stuff. Because I'd never really used Lisp before. And I started playing around with it some more. And then, as a signal processing guy, I was doing some complex arithmetic. And I found out at work we had Spark stations. We're using the Spark version. And I found out that the complex, yes, complex subtraction didn't. I think it actually added instead. So that's a pretty serious mistake. So I dug around and figured out how it was done, and submitted some changes, and like it just went from there. I started hacking more and more, come up with my free time, doing all kinds of stuff, whatever I felt, because open source, you do what you want. Okay, about all this stuff is pretty old. I started this about 10 years ago, so I haven't really touched it in over 5 years. So some of the things are kind of fuzzy, but we wanted to be able to run CMUCL on ARM because it's everywhere, and we have to make some decisions on what the port would look like. And a lot of this stuff was done with help, lots of help from Carl Shapiro, who was the other last lead developer. So, we have to figure out what kind of ARM we want to do in the OS. CMUCL has actually 4 different garbage collectors, so we have to figure out which one we want to use. And you have to figure out how to assign the registers and what they're allowed to do to handle Lisp. So for the target architecture, I think it's pretty obvious. We were going to use Linux, and actually ended up using OpenSUSE for my Raspberry Pi, because at that time, I think that was the only Linux system I could find that actually really supported ARM, or Raspberry Pi. We decided to do the ARM V7A because that was pretty much the most up-to-date version, and you had to have hardware floating point because some ARMs don't have, ARM 7s don't have hardware floating point, but we want to make sure you can do arithmetic, floating point arithmetic in our port. The next step is register assignments. You have a big set of registers, and what CMUCL did for a lot of, well, one thing is you can just have registers can hold anything at any time, and that's we're not partitioning. And of course, since registers can hold anything at any time, you have to have a concerted GC, because if you get interrupt, you need to know what's in those registers so you can find all your roots for the GC. And this is what the x86 port does, because they're just ordinary registers. So partition them in any meaningful way. The other way is the actually partition registers. And this is what all the other CMUCL ports do. So we have a set of registers that say you can only have, these are the only registers that can actually point to Lisp objects. These other registers can hold random stuff. It may look like pointers to memory, but it's not. It's random integers, just random stuff. And because you know what's in each register, you can do a precise GC. You can then find all your roots. This is what we ended up using for the ARM port. We went through, like, I think this is the 4th or 5th iteration designs, and the first 5 ARM registers are non-descriptors, which in CMUCL lingo means they can hold anything, random integers, random values, whatever. But they are not, they're never used as roots for the GC. The rest of the registers are actually descriptors, and these registers can only hold Lisp objects, pointers, immediate objects or pointers to Lisp objects. And these, the names are the actual names in the compiler. It's not that important, and of course, only 15 registers. The last register on the ARM is the PC, and we don't actually keep a name to that one because we don't want the list of cards to accidentally use it for anything because that'll just screw it.
You're saying the names are arbitrary, like someone decided that they don't really mean.
Well, they actually have meanings. Like NO0 means it's a local variable that can hold anything. Most of the other ports have like NO0 through NO5 or 6. Like Spark has NO0 through 6. NARGS is a register that actually holds the number of arguments that are going either into or out of a function. NFP is the number frame pointer where the non-Lisp objects get stored. The code pointer, the code register actually points to the code block that's being executed. These don't always hold there, but at certain points they actually do. AO0, 1, and 2 are used as the argument registers to Lisp functions, so they have to be descriptors. LRA is the Lisp return address, so that's where it's a pointer into the code block where Lisp would return to. Null is actually the nil, it points to the nil value, and that's important in CMUCL because that is used as an offset into lots of little so-called static symbols and static functions, lots of common symbols and functions that are used all over the place. So that way it's quick access to those functions. LexEnd holds the lexical environment. CNAME actually it holds the pointer to a C function. CFP is the code frame pointer. CSP is the stack pointer. And lib is the Lisp interior pointer. So it's a weird register that actually can point inside an object, which you normally can't do because it just screw up GC. So, yeah, so there are lots of names. There are other registers, but because we only have 16, we had to pick some. Okay, for the garbage collector, the original collector was the Cheney stop and copy collector, and that's was the one that's used for all the ports. And of course, when x86 was done, they had to make it conservative. So it's basically the same one, except they made it conservative. Basically, when you look at the registers, anything that points to a list, anything that points into list memory is considered to be a Lisp object, even if it's not. Sometime later, Douglas Crocher implemented a generational collector for the x86. So that was, of course, conservative. And then at some point, I don't remember exactly when, I decided to port that to Spark and PowerPC. And because it has partitioned registers, it's no longer conservative, since you know sorry. And since we partitioned the registers for ARM, we're going to use the generational collector. And the other reason is I don't know if the chaining collector and the conservative chaining collector actually work anymore because we always use the generational one now. So that would just be 100 times more work to figure out if they work or not. For the implementation, of course, you have to, since it's a native code compiler, you have to tell the compiler where all the instructions are. So we have to go and define those. You have to write a bunch of initial C and assembly routines to be able to call in and out between Lisp and C. It's called into Lisp, and you can call into C. And you have to implement flops. I'll get into that later, what those actually are. And then just start building it and just keep iterating until it's done. So to define the instructions, you basically stare at the assembler manual for the ARM, figure out what's common. You have to describe the instructions in a way. There's a pretty nice code to do that in the compiler. And we'll look at what the ARM instruction looks like and how you actually write it in Lisp. And I'll give you an actual instruction definition. So here's like 4 different examples. Like the first one is just adding 2 registers, but in Lisp, every instruction starts with the INST, and then the name, and then arguments. So in this case, you can actually write it pretty much the same way. For more complicated instructions, like the next one, which I think means you're going to do an add, but only if the condition code says it's less than or equal to. And when you do the add, you're going to update the condition codes after the operation, and you're going to add R0 and R1. No, R0 is the result. R1 and R2 are the arguments. I think means R2, you're going to left shift by 3 before you do the addition. And the equivalent Lisp is there. Since we can't use the same syntax, the makeshift basically does what the R2 and LSL3 does. And the LE at the end tells you that it's conditional instruction. And the other 2 are rather similar. And here is a definition for the breakpoint instruction. I picked this one because it's simple and relatively self-contained, because all the other ones are just huge macros because there's so much commonality. It's like all the add instructions have or look very much like sub and other 2 argument operations. This is what the instruction looks like from the manual. So it has a 16-bit immediate value that's split across 2 parts of the instruction. And to get Lisp to describe this, it turns out you'd have to define an emitter, which is tells the compiler like, here are all the bytes in this 32-bit word, and this is the bytes that you're going to fill in with, the bits that you're going to use to fill in the instruction, and it'll emit that 32-bit value to the code. Then there's the instruction format. You have to tell the compiler what the instruction looks like. And it turns out that for this particular breakpoint instruction, the manual actually describes a whole bunch of instructions that have what they call format 0, which have a similar format. And the basic format is there's a condition and there's an op B0 field. And that's what the byte says. This in that 32-bit instruction, it's a 4-bit field starting at offset bit 28, and the op B0 field is 3 bits starting at bit 25. Then you have to, it's a special, then you have to find the instruction. And it's a breakpoint instruction. It inherits from the format base format, and the default printer tells the compiler how to print the instruction. So this one's pretty easy. You print the name, which is colon name, condition, which in this case is always breakpoint instructions, always the condition is always, and then the tab and then value, and then here's the additional fields in the instruction, and the values there are the default values that we give it. And then the immediate 16 field listed as a list so that it knows that there's 2 parts to it. And then there's a special function to gather up those 2 parts so I can print out the 16-bit value. And then to define the actual instruction, you give it the name BKPT, which we try to keep the same as the ARM instruction name. There's a value, which is the 16-bit value. And basically, you call the emit format 0 instruction that you define, the format you find above. And the segment is something for the assembler to keep track of things. And you list out the various parts of the instruction that you define. So there's 6 parts, which is an instruction definition. And if you want to go look it up, there's the actual instructions set in the repo. It's like 3,000 lines of code. It was actually kind of fun to do that. And that's actually quite useful because I didn't know ARM very well. If you write a compiler, to know what all the instructions are. The next step is to implement these things called VOPs. So what is a VOP? And then how do you know which ones you need to write? VOP stands for virtual operation. So it's basically a small bit of assembly that you use to implement an operation. The compiler, because it supports all these different architectures, when it decides like, hey, this bit of code is going to add 2 fixed nums, and I know the result will be a fixed num. So what it does is look up in this table, like, here's how to add a fixed num. And the VOP tells the compiler, here's the set of instructions, and since I defined the instructions, you'll dump those into the generated code. Here is an example of a really simple VOP. You define a VOP, the function define VOP. This is basically a template. It just says that its operation is considered to be fast, so it doesn't cons, and it's safe, so it doesn't return weird stuff, unexpected stuff. And of course, there's lots of operations on signed integers with only one operand, so we define another VOP that's called signed unop, and the argument is always x, and the result is always returned in the register res. And both of these are signed registers, so they're one of the non-descriptor registers that we described before. And the argument types, well, there's only one, so it's a signed number, which in this case was 32-bit signed integer, and the result, it's a 32-bit signed integer as well. And then the actual VOP that actually does this, this one happens to be the log not, which is what the translate is for. So it tells the compiler that this VOP is the translation for the log not function. And there's an emit not implemented. I'll talk about that later. But basically, the log not is the MVN instruction, and you store the result in res. The argument is in register X, and you have to write a whole bunch of these. The question now is, how do you know? I looked up x86, and there's like 600 VOPs. A lot of them are macroized, so that you don't have to write all of them by hand, but not all of them. But of those 600, where do you begin? And the answer is you don't know, because no one's actually written it out. What comes first? And so the question now is, how do we figure it out? Because you don't want to just waste a bunch of time writing VOPs that don't get used until way late. So what we did was implemented not implemented macro, which is what that emit not implemented was. And what it does is it emits an undefined instruction. And after that instruction, we dump a sequence of bytes that has the VOP name. And then as the code executes, of course, this undefined instruction triggers an exception. We wrote a whole bunch of C code to handle the exception and Lisp to recognize the exception if needed. And what that does is basically, when we get that undefined instruction, it prints out the name of the VOP, so we can see that, okay, first bit of code that's run has the VOP name this. So we go and implement that, and then just keep going and going and going as it goes. And debug the VOP if you make a mistake, as we quite often did. So to build it, you have to cross-compile. In this case, we cross-compile from x86 to ARM because that's really the only version that still runs. And I was running on ARM hardware, my little Raspberry Pi, and then you debug it. Then you write more, and then you just keep doing it over and over until you're done. And as far as I know, only one person, not from CMU, has ever done that, and that was I forget his name. Dwayne, I think it was Dwayne Reddick from France. He did a PowerPC port and donated to CMUCL many years ago. I used that as my primary development machine when I had a Mac Mini a long time ago. Okay, so where are we? We've written a lot of ops, and it gets quite a ways loading parts of the kernel. And this will work. Oops. I didn't want to put the current status in the document. I was hoping I could link it up to our wiki that actually has it. Well, we'll see how it goes. And maybe we'll come back to that. So it partly builds. We're a long ways from getting anything to work. I mean, you can't do the build part consists of two parts. It builds the kernel.core, which then uses that to build the final core file. We are a long ways from writing all the VOPs. And I actually got stuck at some point. There's a VOP. I can't remember what it was because this was 2 years ago, but it required lots of registers and of a certain type, probably descriptors, and I didn't have any more, or they were already being used for other things when VOP was supposed to be in them, because the compiler would tell you that. And I just kind of stopped there because it was just. In addition, a few years ago, I saw an article that basically said that ARM is no longer going to do any more of the 32-bit ARM processors. They're all going to be 64-bit, so it's essentially dead. So my motivation kind of went down when I found that out. The other thing we could do is try to go port all this to the ARM v8, a 64-bit processor. And way back when, CMUCL ran on an alpha, but since CMUCL even back then on an alpha was a 32-bit port, what they did was either they had a compiler switch so that it forced all the memory to be in the low 32 gig or 32-bit address space, 4 gig. And then you can run the alpha code that way. And as far as I know, you can't do that on the 64-bit ARM. You can't map the low 4 gig memory. So that's kind of out. And
actually, on OS X, it's not only out, but it's illegal. That's a 4 gigabyte zero page.
yeah, I tried that on the.
That's a recent change.
Oh, okay. I tried it on my Raspberry Pi.
Well, it's common to have a small page for zero, for
No
electric
point.
fence or something like that. But they decided that they wanted a really big electric fence.
Yeah. I tried it on my Raspberry Pi and it won't let you map memory there, so it's not going to work very well.
They're forcing you to use, but they're forcing you to use 64-bit pointers in Mac OS. It's not the case in Linux or anything like that, but for security reasons, they're forcing you to be 32-bit clean, I would say.
Yeah. Yeah. If anybody knows if there's a way to do this, that would be really helpful.
Why don't you just go straight to 64?
I'll get to that too. And like on the x86, you can run 32-bit x86 code on a 64 processor. And that's supported. But as far as I know, no ARM OS Linux version actually supports that. I've seen that there's a lot of stuff has been done, but they've never actually finished it. So we can't actually run it that way either. And of course, going to a 64-bit port is very, very hard because the cross compiler isn't really clean and lots of things leak. And fixing all those, lots of information was the host leaks into the target and it messes it all up. Way back when, someone had started doing a next AMD 64 port, and I got it going part way, far enough to get to the REPL on the 64-bit port. But when you did some arithmetic, it was all messed up because the size of the fixed number were still 3. It thought the size of the fixed number was still 32 bits. So then I just stopped working. That particular code base is now so old. It was all done on a branch. It no longer works. But yeah, we definitely do we would actually want to have a 64-bit port. But that's going to be a lot. Final thoughts. I got an email just the other day from Paul Bukowski, who is the person who actually finished the x86 port, and he was porting from alpha to a FreeBSD system. He told me that about this time, 30 years ago, is when he started. So this is the 30th anniversary. Come on. I wish I could have had ARM. I wish I'd known. I would have worked a little bit harder to get an ARM port maybe going as a celebration, but that didn't work. Do I want to finish the ARM port? I don't know. It's kind of dead. I haven't touched it in almost 10 years. I mean, the ARM v7s and things like that are kind of dead. Just kind of lost motivation. I did learn a lot because I touched parts of the code that I never really had to because it was always done. We should probably get the x64 working. Can't stay 32-bit forever. And once we get the x64 working, it'll be a lot easier to cross-compile to other 64-bit OSs because you have some base that works. And Carl is working on that, but I don't know how far along he is. Another thing would be kind of nice to revive the Spark or PowerPC ports, but that requires working hardware or an emulator. I can't get the emulator to work. And all of my Spark PowerPC machines are kind of dead. So if you want to see more about, CMUCL, you can visit the CMUCL.org website. It has links to everything and documentation and wiki and repo and everything. If you want to see a little bit more about progress on the ARM port, you can actually go to Bitbucket, where we actually did the original work. It all got ported to the official repo not too long ago. Okay, here is what running, what it actually looks like. So the compiler prints, the code prints out global DB in it. So it's initializes some stuff. And you can see here, it says not implemented. And I think the first swap is called allocate full call frame. So that's the first swap we implemented. And then the next one is define load constant and all of these. And, we made progress. And I kept adding more and more until here, right? I don't remember anymore. So Yeah, that was it. It was a lot of fun. I enjoyed it. But it is a ton of work. Again, I think I'll spend my time at 64 because it's everywhere. All right, thank you.
So if someone got it in their head that they wanted to complete this port, what would you tell them?
Go for it.
Would you give them advice if
Oh,
they?
of course.
Yeah.
So if you're interested, talk to me and we can hook up with Carl and everybody
And if they saw your V7 work, how much of that could they make use of for V8? Would it just be not useful at all, or could they follow a pattern or have ChatGPT convert it?
the hardest part is defining, I mean, it's not super hard, but it's a lot of work. And that's defining the instructions and V8, V7 are very different.
Mhm. I have, okay.
It's just a ton of work, but it's not super difficult. It's just reading a manual, figuring out what the instructions are.
That sounds like a job for AI.
You have regrets you did it? I mean,
No,
you're happy you did it.
yes, because it was really fun learning the ARM architecture, which I never had before. I got to look in large parts of the code, like all those registry names, they were just random names to me. Because I never had to deal with the calling conventions and all that. Most of the MOPs I wrote, writing MOPs is fairly straightforward because you don't need to do lots of these things, except for the hairy call conventions that are used. It was a lot of fun, and I really enjoyed it.
Because CMU Common Lisp was used everywhere for decades. I mean, it was really, really useful to a lot of companies. You know, we were using it almost 20 years.
Oh, wow.
So, you know, I mean, it's a noble effort wherever it goes, right?
Yeah, I mean, most of this, I can say, a large part of it now is done in SMCL because they have this huge army of people. I don't know where they get them all. But yeah, I mean, they ported it to ARM, and I think they have a RISC-V port that someone did. So it's over.
Two questions. One, what is the relationship between CMUCL and like the institution of the University of Carnegie Mellon? And then two, is there anything about this like VOPS like infrastructure that you feel like is like a very valuable insight worth sharing, or is there anything about it you would change? Like, you know, just kind of as you spent so much time in that place that not a lot of people have been.
So let's start with the first question was the relationship between the university and CMUCL.
Yeah.
Of course, I mean, it came from there and it was a research project. They did a lot of work. And by the time I got involved, they had stopped working because I think they lost funding and they were now working on Dylan at that time. I talked to Rob McLaughlin a lot, asking questions about how things work and why did this happen, why did this crash. So that was really useful. But of course, as the years went on, he remembered less and less.
So it's just historical
Yeah,
at this point.
it's just the name. I mean, that's why I think that's how they came up with the name for SPCL, Steel Bank. This is Carnegie Mellon.
So SPCL is a derivative of CMUCL. Yeah. Just to be clear.
We worked together for a bit. Separated, and the big thing about it at the time is that someone went through and actually, I think he actually was able to cross-compile from CLISP. So he went and made all these changes so he could cross-compile from a different compiler.
Wow. Is there a pun in the name Steel Bank that I'm missing?
Because it's Carnegie Mellon. Carnegie was the steel guy, right?
How
I
many,
see this way.
how many bops are there?
I counted, I think there's, like I said, I think there's like 600 some blocks. But a lot of them are macroized, like, you know, all the arithmetic operations that take two arguments, you can just write a big macro and just generate them all. It's not 600 different blocks you need to write. You just need to write.
So it's comparable to say LLVM.
That I have no idea because I don't know anything about.
So did you have any big thoughts, like while you were working with the bops and turning them over, like, oh, I wish they'd done it differently, or like, oh, that's so smart, they did it this way?
No, I was basically just, this is how it's done, and I just wanted to get the report done. And maybe after I finished, I could say, okay, now that I've done it all, I can look back and say, oh yeah, well, this would be nice because I could have done this or that. But I think the guys at CMU did a pretty good job with making architecture independent. But I'm not familiar with how anyone else does it. If Carl were here, Carl Shapiro, he knows the ins and outs of all the different Lisp versions out there, so he could give you a much better idea. So I just don't know. I'm not suffering.
You kind of software guy. You can't believe that. Any other questions? All right, well, thank you, Ray.
Thank you.